Hello everyone, and welcome to my presentation, which is about managed code rootkits. My name is Erez Metula. I'm a secure software engineer working to Be Secure, a security company, and my work there is I'm a manager of application security department. My work involves performing application level penetration testing, code reviews, SDL, and I think one of the most important things that I do, I teach developers how to write secure code. And today we're going to talk about application level rootkits. And before we start, let's start with a little bit of demonstration. Let's start with a trivial question. What should the following code do? Well, we see one line of code. We see a piece of code in Java. The code is supposed to print, right? We have one line of code that says system out print line hello world. Let's run this kind of code and let's see what happens. So now I'm going to execute the same code, and running the code gives us this output. So basically, I have something that changed the implementation of the language. Well, the code says print the string just once, but instead it's been printing it twice. Why do you think things like this could happen? Things like this could happen because I changed the internal implementation of the language, of the Java language, so that the function that says print line, the internal implementation of print line was modified. So performing code reviews on the application level code will not detect things like that. And this is what our presentation will be about. This is just a small proof of concept, a simple proof of concept of language modification. What we're going to talk about today, we'll start with an introduction to managed code execution model. We'll see what's so special about managed code. After that, we're going to talk about managed code rootkits and what are the advantages of rootkits at managed code, what I call MCR. After that, we're going to talk about application level virtual machine modification and malware deployment. We're going to talk about very interesting attack scenarios, and we have a couple of demos so that we can see how things like this can happen. And we're going to see at the end a very cool tool that I've developed called Net-Sploit, a custom .NET framework language modification tool. Basically, you can extend this tool to modify other languages so that you can inject code into the language and change the implementation of the internal level code. Well, a little bit of background. It all started with a little bit of playing that I did back in 2008 about language modification. Basically, very fast it led to changing of the .NET language. I wrote a white paper called .NET Framework Rootkits, backdoors inside your framework, that shows how you can do stuff like that. I presented it in Black at Europe and in ConseQuest. But the thing is that .NET Rootkits was just a case study. And here we're going to talk about today about the general case of managed code rootkits. And we're going to talk also about the Java rootkits, for example, so that we have the full picture of the problem. Let's start a little bit about managed code. How many of you guys know what managed code is? Thank you. Well, managed code, this is code that runs under the management of an application level virtual machine. We're not talking about OS level virtual machine. We're not talking about VMware or stuff like that. We're talking about application level code, application level virtual machine that hosts our code and translates the code to low level assembly language. Low level assembly language is being transformed from high level intermediate language. Intermediate language, high-level intermediate language, let's see an example. This is how intermediate language looks like. Basically, it looks very like assembly language, like low-level assembly language, only that it's something which is virtual. If I give that instructions to the CPU doesn't understand what intermediate language means. This is the part that should perform this kind of translation. This is the virtual machine part of doing that. So that we can see that the executable that we see over here, the code, the higher level, intermediate level code, will be transformed using the machine-specific virtual machine, so that I have specific virtual machine for Windows and for Linux and for mainframe, for all of the systems that I want to execute my code on. And the virtual machine will transform it to the low-level assembly language. And when we're talking about managed code platforms, let's talk about a little bit of examples. This presentation today talks about problems that can be applied to all of those languages that we see back there. We're talking about Java, JVM, .NET CLR, we're talking about PHP Zend engine, we're talking about Python. Basically, most of the languages that run managed code are affected. And basically, today we're going to stick with Java and .NET as case studies. Basically because the model is very similar and similar to other languages, and it's very easy to understand their model and to use the concept on other platforms. A little bit about Java execution model. Basically, we have 3 layers. One layer, which is the application level. This is where the code, this is the application level code. We have the Java JVM. This is the layer that performs the translation to machine-specific code, and the OS. Well, not like languages, for example, like C++ or C, when our code runs directly on the CPU, the instruction set inside the code is assembly language. Here we're talking about machine-specific code. So Java code is being compiled to bytecode. Bytecode is being hosted in the JVM. The JVM loader loads the class, fetches the machine code from the Java jars, the class libraries, perform JIT, just-in-time compilation, translate it to machine-specific code, and give that to the CPU. And this is what the operating system sees from his point of view. It doesn't really care that it's a Java program, that is specifically Java executable that is running. Basically, the same is true for .NET. The model is very similar, only that .NET code is being compiled to executable to what is called in .NET notation assembly. Assembly is either an executable or DLL. This piece of code contains the high-level intermediate language, the MSIL or CIL. And basically, this code is run on the CLR. The CLR is the equivalence of Java JVM. And the code is being fetched from the GAC. The GAC, the Global Assembly Cache, this is where the DLLs of the .NET framework are installed. And basically, this is where the DLLs are being loaded based on their signatures, which is called in .NET strong name. And after the DLL is being loaded, basically the same things happens. Code is being translated using the jitter to machine-specific code, and this is what the CPU sees from his point of view. When we're talking about managed code rootkits, and now let's move on to more security stuff. We're talking about application-level rootkits that are hidden inside the virtual machine, so that the virtual machine is being customized, malware is being deployed inside the virtual machine, so that the virtual machine lies to the upper-level application. The application, which receives services from the virtual machine, well, it receives services that are being changed. The services are no longer the same like there was before. So managed code rootkits, they target the virtual machine so that the influence is on the upper-level application. And basically, managed code rootkits, MCRs, they can do all of the things that kernel-level rootkits, for example, the traditional do. For example, they can hide files, hide processes, hide registry keys from the application, right? Not for the operating system. So the application cannot see this kind of stuff. But they can do also very interesting things that are related to logical manipulation, so that we can do very interesting logical tampering stuff that we see later on. The advantages of MCRs, well, basically, this is an ideal overlooked place for attackers to hide their code. Well, one thing is that no current antiviruses, no current host-based intrusion prevention systems, they don't understand higher-level intermediate language. They don't know how shellcode looks like in intermediate language. They cannot have things like that. They must run it or must pass it and evaluate it in order to know that. The same goes for forensics. Well, forensics today, they do not check inside virtual machines, and this is the place that they should do that. And another thing is that developers' backdoors, now we're talking about malicious developers that know that their code will be security audited, and they know that some auditor will look at the code that they are writing. They will not hide their backdoors inside the application level. They write it downstairs, the virtual machine level. Another thing is that MCR can provide universal rootkits. Because of the fact that virtual machine perform the universal translation to machine-specific code, the attackers can write their malware in the high-level virtual machine language, and the machine-specific virtual machine will perform the translation for them. So we're not needed to talk about specific addresses or specific memory sizes and stuff like that. The universal rootkit can do it for you. The virtual machine will do it for you. MCR have also a large attack surface because virtual machines are pre-installed on newer operating systems. Newer version of Linux or Windows contains the .NET framework, contains the JVM. So basically most of the machines out there contain some kind of a virtual machine. We also have a high success rate because if you want something to happen due to an executable of some specific code, all you need is just one executable that will target the code that you want to run. And of course, managed code becomes part of the operating system. We see more and more things from the operating system that are being implemented as managed code. For example, .NET PowerShell commandlets. And MCR provides us the ability to perform a very sophisticated attacks. For example, using a low-level access to very important methods inside the virtual machine. It enables us to do timing attacks. We'll see later on how timing attacks can be used, for example, when an application will open a connection to the database. And it enables us to do another interesting thing, which is object-oriented malware. Using the fact that object-oriented provide us tools for like inheritance. So basically we can use this behavior to inject code into some specific classes. Well, basically it looks like this. If we're talking about language modification turns into rootkit development, basically if we have here the higher-level application which calls some specific low-level runtime method, this is a method, this is like the print line that we've seen before. Think about it like system calls that the operating systems are giving us, only that here we're talking about services that are being given to the application. Well, when we are doing language modification, basically the runtime method, the one over here that is being called, well, in rootkits, we are throwing it away, changing the method to something that will do something completely different. Now that when a call comes from the application level, remember the application does not change, the application stays the same. Now that the call comes, it will do something completely different and our system will be hacked. So, looking at again an example of the same thing that we did in Java print line, only now that we're doing it in .NET. In .NET the equivalence of print line, this is called write line. And basically if this is the original code of write line, and again, this is just a simple proof of concept code. All I had to do is just double the code, and this is the higher level intermediate language code. All I have to do is double the code so they see basically that now the modified write line method contains 2 blocks of code that will print the same string, right? As you can see, I had to change a little bit the code, recalculate addresses. Basically, now, and this is a very simple example, when we are talking about huge amounts of code, this is a very intensive task of recalculating addresses, modifying them, changing jumps, and stuff like that, right? We'll see later on how Net-Sploit can help us to avoid this kind of recalculation. Okay, when we're talking about the attack scenarios, there are basically 2 attack scenarios that managed code rootkits are being involved. Well, managed code rootkits require an administrator level privileges in order to perform, right? So one of the attack scenario is this is an attacker gains control to the system, he gains control to the system with any kind of vulnerability. So now we have control on the system. What's next? Attacker will usually want some kind of he will usually use some kind of a post-exploitation attack technique, so that he will have complete control of the system. He will have a control on the system maybe on later times, maybe when some important data will be on the system. So basically this is another post-exploitation host-keeping attack vector, right? Housekeeping attack vector. The second scenario we are talking about the insider threat. Here we are talking about those guys who have control to the system. We're talking about developers. We're talking about IT managers. We're talking about DBAs. Those guys do not have to steal the administrator password, they already have it, right? So guys like those which are basically not, most of them are not malicious, right? But there are those that are, that might take advantage of this access and to install MCRs. When we're talking about implementation techniques, there are two ways of implementing MCRs. One is what I called a non-evasive technique or by design, and another is called evasive technique. Non-evasive techniques, this is when the application level framework lets you do it deliberately. For example, using AOP, aspect-oriented programming lets you change and lets you attach code, pre-code, post-code to some specific method. So this is by design. You don't have to modify code to do that. The framework lets you do that. We're talking about configuration modification, for example, setting an alternative evil class loader, for example, loading a malicious agent in Java. This is how you do it. For example, modifying the machine config in .NET. All of those ways let you do the same thing that we're doing here now, only that can be easily seen. And in evasive technique, when we're talking about modifying the virtual machine so that the application cannot detect it, we are talking about the ways in which we can lie to the application and hide the presence of the malware that is running inside the virtual machine. So, an example of Java rootkits. This is an example of evasive technique, what we're going to see now. This is just the steps, the basic steps. Well, first thing that I would like to do is usually change classes inside rt.jar. rt.jar, the runtime classes, this is where most of Java important files are located. So first thing that I would like to do is go to rt.jar and extract class that is very important to me that I want to change. For example, the one that I did with print line twice, what I did, I changed the class printstream. Printstream, which is located in java.io.printstream, is located inside the jar in the directory Java, in the directory IO, and back there I can see the class. Extracting the class out can be performed using the jar executable, so jar xf will take the file out. Next stage, I would like to disassemble it. Pay attention, I'm not decompiling, I'm disassembling. If I would do a decompile, I will have Java code. But the thing is that I will not be able to recompile it again because of dependencies. I don't have the classes that the real class is referencing. So I will disassemble it. I will disassemble it, get some code, get some Java, for example, get some high-level intermediate language, change the intermediate language, reassemble it back, and throw it away to the classes. Basically, I need a good disassembler. For example, Java native disassembler, Java P is not good for doing that. I need disassemblers, for example, the Jasper and Jasmine can perform the disassemble and reassemble back there. So first thing I'm doing disassembling using Jasper, and after that, after changing the code, I'm doing assembling using Jasmine, and after that I'm getting my class. This class is this is the modified class, and I'm taking it and I'm putting it away again in RT using jar UF. So this is how a modification of one class can be done. For more information, you can go to the site, to applicationsecurity.coil, Java Rootkits, and have more information about it. Well, .NET Rootkits are a little bit more complicated. Well, in Java, we didn't have any signatures to mess with, right? All we had to do is change the code. In .NET, the modification is a little bit harder. Well, although I need to deassemble the file and reassemble it, now I have what is called the strong name, so I have a signature of the file. I cannot just take the file and put it away in the place that I want, because the framework will tell me, hey, you have a DLL with the wrong signature. It's not okay, I'm not going to use it. So in the beginning, what I thought is that, I thought to myself, I need to disable the signature mechanism, right? I have a complete control of the system, I can disable anything. But I thought about something else, and I did a little bit of shortcut. I found out that the way of checking the signatures is not performed during the loading of the file. the signature is just being used as a file mapper. So that if I'm looking at the GAC, this is where the DLL was allocated, in C Windows Assembly GAC32. Over there I see the directory called mscorelib. mscorelib is the DLL that I've changed, one of the most important DLL in .NET. And inside of there is a directory with the version, underscore, underscore, and the signature. The thing is that the signatures is being used just to map the correct location in the directory. So if I change the DLL inside the directory, the framework does not care. So that this way it lets me to just write the file, modify it, and this is a shortcut because, and this is basically because of performance issues, the DLL is not being checked each time it's being loaded. Again, for more information, you can read it in the paper. Well, let's move on. When we are talking about malware development, there are things that we'd like to do to make life easier. For example, a specific behavior that I want to do over and over again. So I can just extend the language. Let's extend the .NET language. Let's extend just not .NET, sorry. Let's extend the virtual machine. Let's add new method to the machine. So basically, I've extended the language. This is what I call method injection or function injection. And basically, I do it because I want to use some functionality, but I don't want to write the code over and over again. I wrap it as a function, and now all I have to do is pass the parameters that I want the function to use. Let's look at a couple of examples. Send to URL. This is where you want to send some information to an attacker. So all I have to do after implementing send to URL is just say where I want to send the data and what data I want to send. A couple of more examples. Reverse shell. Where do you want to open it and which port? Hide file. Inject class. Man in the middle, very interesting. It returns, you say on where you want to open a man in the middle attack, and it returns a socket and keylog events. So basically, those are examples that most of them will be used later on. Well, one of the interesting things about virtual machines, that most of them are utilizing object-oriented concepts. And in object-oriented concepts, we have the notion of extending some classes. Basically, all of the classes are inheriting their behavior from the upper class that they're extended. And all of the classes are extending, basically, a class called object. So if I'm injecting code to object, well, I'm injecting the same code to all of the classes, right? So injection to object means that object-oriented will play its role, and my code will be inherited to all of the classes. If I want to inject code to some specific branch of the tree, well, object is in the root of the tree, but maybe, for example, I want to inject code only to classes that implement, for example, a window. We have some differences of windows, so I will inject it only to a subtree of the whole inheritance classes. Talking about malware development scenarios, when we are changing the language, we can do things which are very interesting. Very interesting attacks can be devised. And let's see a couple of them. Well, the first thing, this is about authentication, credential stealing. Well, what I did is I did something like this. And let's go to the next slide. I'll go back here. Well, this is one application. The target here will be a server-side application, a server-side website. The server-side website implements some kind of an authentication page. The authentication page contains a place for the user, so he will enter the username, password, and a login button. The login button action is being utilized using a method called button login. And in button login, it receives the username and password and sends it to the framework, to the virtual machine specific method that will return the answer, the Boolean answer, whether the username and password is correct or not. So a call has been performed to low-level authenticate method. What I did is I injected code to authenticate, so that at the end of authenticate, I added one single line of code. This is how it looks like if I'll reverse engineer after I injected the code. And it contains a call to send to URL, my send to URL, the one that I've injected before that, so that the data, username and password, will be sent to the attacker. From the user point of view, everything looks fine. If the username and password is okay, he will be let in. If it's not okay, he will receive some kind of a string that says, well, you're not authenticated. Everything looks fine. What I did is that I've injected this code. Well, authenticate, the method that contains the authentication, I've post-injected it, these lines of code. This is the intermediate language code that says, well, call send to URL. I can see the call to send to URL down back there in the forms authentication, and I'm passing there username and password. Well, this is an intermediate language. Username and password is being represented in parameter number 0 and parameter number 1. So basically now I'm sending the username and password to the attacker. Let's look at an example of this. And let's run the same application. So now I'm having 3 players. I'm having 1 user, 1 server, and 1 attacker, right? So the user will be used just for entering username and password. So let's wait a little bit until it wakes up. Yeah, okay. So this window represents the user. Let's put him over here. And let's take 1 victim. Let's put the victim over here. This is the user, the server, and let's add the attacker. And the attacker contains a page. The attacker contains some directory. Do you see the received input? Received input will write down there a file called input that says that all of the data that will be sent will be written to this directory, so that when authentication will be performed, let's put the server over here and the attacker over there. So when the user will authenticate, let's look for the authentication. So first time I'm going to just write something which is wrong. Let's write blah, blah, login. Pay attention to what happens over here at the attacker side. Input was created. Let's perform another authentication just to see that from the user point of view, it behaves like it's supposed to be. So deliberately I will use the correct username and password, 123456, login. Well, I've been logged in, great. Let's go to the attacker side. Let's go to the machine of the attacker, open input, and I can see that user Erez tried to log in with password blah blah, and after that user Erez tried to log in with password 126. So basically this is because the code was injected into the virtual machine code. If I will take a look at the application level, there will be no signs of send to URL, right? So basically this is a backdoor to the send to URL, to the authenticate method. Next example, again on authenticate, we can perform another kind of attack vector on the same method. This is when we're talking about backdoors that relates to what I call magic values. Well, developers usually like to have some kind of a way of getting into the application when, for example, the user forgot his password. So they generate some kind of magic password. This is the kind of password that opens everything. So this kind of password can open each kind of the users in the system. Basically what I did, I added the same thing, and I added code that says if password equals magic value, and this is how it looks like in the intermediate language representation, in the low level in the intermediate language, if the password equals magic value, return true. And if I decompile it, it looks something like this. This is a pre-injection, because here the injection is being performed at the beginning of the method. Another example is reverse shell. And in reverse shell, I'm injecting an implementation of reverse shell into the framework so that I want that when specific functionality will be executed, a reverse shell will be opened to the attacker machine. So, and in this example, I've injected the code to a method that I've injected called reverse shell that will open back a connection to the attacker when executable, when WinForm application is being executed. So I've injected it into run, the run method. And the injection occurs over here, and it looks something like this. So this is the code that will execute and open a reverse shell to the attacker address, to the attacker port, and basically call my method. We'll see an example of this later on. And another very interesting attack, which is attack against the crypto libraries. Basically, attacking crypto libraries is very interesting. Attacking crypto libraries, for example, performing key fixation, for example, performing key stealing, algorithm downgrading. For example, the application is asking to use AES encryption, but in return, the framework performs the encryption using the easily crackable DES. Well, the worst thing about messing with crypto libraries is that they're giving false sense of security. False sense of security is one of the worst things that we have in security. So, for example, and over down here I can see an example of generate key. Generate key is an internal method that will generate a session key that will generate a key, for example, for using the PRNG, so that the application will just ask, give me an encryption key, and it will be given using this method. I'm throwing away the implementation and writing something like this. So the generate key will just return a fixed key. And the bad thing about it is that from the user point of view, data is encrypted. It looks encrypted, right? It looks encrypted. Only that the key that he's using is not effective. It's the attacker-controlled key that it's being used over here. Talking about DNS manipulations, this is where we want the attacker wants the user to connect to some specific machine, not the machine that the user, that the victim wants to get connected. So now we're talking about manipulation of the DNS queries. We're talking about resolving the wrong addresses. Performing the resolving is using in .NET. We're talking about a class called DNS method get host addresses, receiving a host name, returning back an IP. And in Java, we're talking about the class inet address and get by name. So what are we going to do now? I'm going to inject, and this is an example on Java. This is a Java rootkit. And now I'm going to inject code into the Java JVM that when a resolving for a server called www.forexquoteserver.com will be issued, the answer will be returned for the IP of www.attacker.com. So basically, we're doing some DNS manipulation over here. And the interesting thing is that this is a conditional resolving, right? We only want the DNS of quote server to be changed, not all of the DNSs, not all the resolving to be changed. Well, it looks something like this. If this is the function that was before, this is the original inet address, get by name method, I just added code at the beginning. So basically it looks something like this. If you take the file and decompile it, you'll see something that said if s equals forex server, just change s to be attacker. So and let's look at an example of this. Let's take a look at in the next example, we're talking about a scenario in which we have a quote server. This is a forex quote server. And we have some broker that buys currencies, that buys currencies according to the quotes that he's receiving from the server. And in this example, the attacker's mission is to make the victim to buy a specific currency. For example, let's say that there is some business case in which he wants the victim to buy, for example, British pounds, right? So my next example, we're talking about Java, but not just Java. Now I'm going to inject it into a Linux machine. Well, not just any Linux machine. I decided to take a backtrack machine, right? Backtrack is great, but now I'm using it. Usually I'm using it as the attacker machine. Now, for the twist of it, I'll use it as the victim machine. So now I've changed the implementation of the DNS resolving into this machine. So now I'm having my victim over here, and I'll take the server. I'll add the server, my attacker, sorry. The attacker contains a man-in-the-middle server. So now, when a connection will be performed, the connection that will be performed from the client application will be redirected to the man-in-the-middle server. So let's put everything in place. Let's put all the three of them. Sorry. Okay. Let's put it in here. Let's start the server. Let's start the man-in-the-middle server. And let's start the client. Pay attention that the client wants to connect to forexquoteserver.com. Let's do a connect, and if everything works fine, the color will be changed to green in all of the places. Basically, as you pay attention that I have 3 different machines. So, doing a connect. Great. Now I'm connected. Man in the middle has got his connection, opens another connection to the server. The server receives the client. He sees it's the real user. Well, basically now he's started sending quotes to the user. So I can see the values that are being sent. The user receives those kinds of values. And the man in the middle also sees them. So man in the middle can seize the data, and he can also forge messages. So now all I have to do is say something like, let's take bound. Let's say that this is the value that I want him to believe, and USD. He sees this value, you can see it over here, and he says, well, this is a great value, I want to buy, give me 10,000 of those, and from the server point of view, he got it, he got the incoming message, he got the message, transaction accepted, game over. The user has now lost all his money because he made sure that the money that is changed, that the value has been forged, he doesn't know about it. Basically, what I did here is that I took the user to a different machine. Well, of course, if there was some authentication, mutual authentication involved, or crypto, SSL, stuff like that, the problem would not be there, but this is not the point. Taking the user to somewhere which they did not want to go is bad enough to happen, so we don't want stuff like this to happen. Well, stealing connection string is another interesting thing. Well, now we're talking about stealing data from specific classes that contains some interesting data. For example, opening a connection to the database. When we are using the class SQL connection, this class is responsible for opening connection to the database. It contains something, one of the most important data that application has, which is the connection string. We want to steal the connection string from from the class internal class members, from one of the variables called connection string. And the thing is that I'm not just taking it when the constructor is being called, I'm taking it when open is being executed. Why am I not injecting the code into the constructor? Does anybody knows? Why am I not stealing it from the constructor, I'm stealing it from open? The answer is that the constructor, probably the value of connection string is not initialized. And when open will be executed, connection string is already initialized. And this is the reason, this is the timing that I talked about before. So basically what I did is just I called send to URL and send it to the attacker. Another interesting thing is that we can use permanent XSS, permanent HTML injection. Classes contains template, code template of HTML, of JavaScript. If we can inject into those kind of templates, we can perform proxies, man-in-the-middles, defacement. We can even inject one line of code that can connect to browser exploitation frameworks. For example, injecting one line of code that connects all of the user to XSS shell, right? XSS shell using one line of code in the template, all of the users will be affected. Picking into secure strings, well, secure string, this is special strings that contain encrypted data. Secure string says, the logic behind secure string is that if you have some sensitive data, some sensitive string that you want to keep it encrypted in memory, use secure string. Well, the reason why I'm picking into a secure string is that it will probably contains valuable information, right? If the developer chose to use secure string over regular string, this is because he had some reason of doing that. So it will make sense to look at secure string when, for example, send the data using send to URL. And the last scenario, now we're talking about disabling security mechanisms. And now we're talking about code access security. This is like access control list, ACL. The same like the operating system has ACLs for processes. Now we're talking about ACL at the application level for pieces of code. In JAS, it's called JAS, Java Authentication Authorization Server. In .NET, it's called CAS, Code Access Security. Stuff that looks something like this. This is the declaration of security of some piece of code. Well, I can change the implementation of the code that check this configuration, right? So if, for example, a security configuration audit will be performed, security audit will look at the configuration will look fine, but the application will not behave according to this configuration. The application can do things completely different. Again, false sense of security can be achieved using that. So, bad thing that can happen. Well, up until now we talked about scenarios that can happen. And when we are talking about scenarios that can happen, we can take advantage of advanced topics. For example, the way of which virtual machines translates our code. We can actually write classes that contains general purpose code that can be deployed in different platforms. The same class that was used on Java, for example, on Java Windows machine, was deployed later on Linux. So the attacker does not have to write his malicious code for different kinds of platforms, right? He does not have to write code in assembly language or for Intel after that, for Motorola, maybe CPU, or maybe some other platforms, maybe some other things will change. So basically, same class can be used on different platforms. Another thing is that runtimes are using virtual machines. For example, we're talking about ESB, we're talking about web services stacks, databases, application servers. All of them can be changed. For example, SQL Server 2005 contains an embedded version of .NET Framework. Did you know that? Did you know that, guys? How many of you guys know that? That's it? SQL Server 2005 contains an implementation of .NET Framework. So basically, we can change the implementation of the database. So it's not just restricted to application executables. We can do very interesting things. Think about it changing the meaning of select, for instance. And another interesting thing is that MCRs can be used in a second-order attack. And in second-order attack, now we're talking about second-order rootkits, in which we have OS-level rootkit, traditional OS-level rootkit, maybe a kernel level, maybe some driver, that hides the traces of managed code. Well, managed code rootkits have their own traces. Think about it. MCRs does not lie to the application. Does not lie to the operating system. They lie to the application. But still, they have traces at the operating system level. File size changes, signature changes, stuff like that. But OS-level rootkits can cover up MCRs, and MCRs can cover up the traces from the application. This is the second level order that we can achieve. So up until now, we've talked about the theory behind it, and let's look at the tool that will enable us to perform code modification, language modification. Well, I've developed a tool called Net-Sploit, and Net-Sploit enables you to change a specific language that you want. Basically, now it can do it for .NET, but it is very easily can be easily customized. Well, what Net-Sploit does, it can extract the file from the GAC Well, now it can extract DLL from the GAC. Tomorrow it will be able to extract class from Java jars and basically stuff like that. It can perform all the complicated modification, disassembling, injecting new functionality, injecting payload, doing some code modification, line recalculation, all this stuff, and recompiling it back and install it back into the virtual machine. And well, basically what I did is that I implemented most of the things that we talked about today as a Net-Sploit modules, so you can use them. Well, the Net-Sploit modules are a generic concept that separates the development of modification into basically 4 stages. Well, one stage, this is the function, so you can write general purpose function. It does not specify when it will be used. This is just a general purpose function, a method. You can develop a payload. This is the injected code that will be injected into some specific DLL. You have references. This is when you're injecting code that now must use some external DLLs, but the DLL does not have a reference, so you are injecting the reference from outside. And we're talking about an item. Well, an item is a description of an injection. An item basically looks something like this. And this is a very simplistic overview of an item. Basically, an item contains a couple of information. Well, it contains a description of an item. This is less important, but it contains stuff like what is the target, basically what you want to change. So what is the name of the DLL and where it is located. This is the where. After that, we're talking about the what. What you want to inject, what kind of function you want to inject, where you want to inject it. So for example, if I'm talking about a payload, now I'm talking about a file called writeline to us.payload. Basically, it looks something like this. It contains the payload that I want to inject. So all I have to do is have files that contains code, and now all I have to do is just mix them. I'll specify in an item what I want to inject. And the last thing that I have in an item, the last important thing, is the mode of operation. Well, mode of operation specifies whether I want to inject the code in a pre-injection manner. For example, if this is the method code, original code, maybe I want to inject it at the beginning, and this will be a post-inject. Maybe I want to inject it at the end. This is a pre-inject. And the third option is replace, when I want to throw away the implementation and write my own code. So it lets me do some very complicated injections. So basically, I can change any language that I want. Well, it's not just restricted to security, right? I can customize I can make my own version of, for example, the .NET framework. I can make my own version, my customized version, secure version, maybe a more optimized version. So it's not just for security. And let's take a look of an example of usage of Net-Sploit. And in the next example, we're going to use Net-Sploit in order to perform a very complicated task. This is to show you the power of Net-Sploit. We're going to inject a reverse shell, a conditional reverse shell, in which a reverse shell will be opened back to the attacker-controlled machine when a specific application is being executed. For example, an application called sensitiveapplication.exe. This is the logic. So let me show you the UI of Net-Sploit. Let's go back this machine. And now I've executed the Net-Sploit. In a second, we'll see the UI of Net-Sploit. This is how Net-Sploit looks like. So what I want to do next, I want to load an item. So now the directories, all the items will be opened, and basically I can see here many of the described attacks that I talked about before already have an implementation, a module of implementation of Net-Sploit. let's pick one of them. I will pick the conditional reverse shell into WinForm application run. And now it shows me the data that is specified inside this item. As you can see, it contains information about where I want to inject it. So this is the name of the DLL, where it is located, what is the native image location of it, which function I want to inject there, which kind of payload I want to inject, and the mode of operation. Let's start the injection. And now it will perform the very intensive task. It will start with taking the DLL, extracting it from the GAC, copying it to some temporary location, disassembling the file, get the MSIL code, injecting the first method of reverse shell underscore generic. After that, inject a method called reverse shell private generic. After that, inject the payload into the place that I said I tell them to inject into method run, right? I could inject to any place that I want. I also set it to do it in a pre-append mode, and when everything is finished, it will recompile it back, but we are not finished yet because it's not being deployed. When .Net-Sploit will finish its executable, it will give me a DLL. But the DLL is not used, right? The development with .Net-Sploit should probably be done not on the victim machine. So basically now we have the DLL, we want now to deploy it. .Net-Sploit can generate deployers, batch file deployers, deploy.bat and undeploy. So that all you have to do is take the DLL and take the batch file to the machine that you want, and you can deploy it over there. You don't need .Net-Sploit on the other side. Until it's finished, it will take a little bit of time because I've lowered down the memory for this virtual machine. Basically, I'm running 4 machines now, so now it will take a little bit of time. As you can see, it finished the decompiling, it's injecting the method. And let's talk a little bit about how it's been implemented. So basically, .Net-Sploit modules, they are located inside a directory called modules. So here I have, for example, the payload. This is where the payload is located. So basically, I can see here all the code, all the payload code. So this is the generic code that I want to inject. I have a directory for functions. This is for method that I want to inject. For example, I can see the function of a reverse shell, for send to URL. When my application, for example, I send the username and password, I made a call to send to URL. This is the implementation of send to URL, right? The code that calls send to URL, and this is the payload, this is something that looks something like this, okay? So I have everything in place here, and of course I have the items, and the item for the thing that I've just run now, well, let me see if I have it here. This is a different machine. Let me show you over here. An item, conditional reverse shell. This is how it looks like. Before that, I show you a very simplified item. This is just for you to see how an item looks like. Basically, it says, well, I want to inject a function, and this is the location where I want to inject it. I have another function. I can see it's an assembly func. Basically, as you might see, the language of .Net-Sploit, this is a specific language that you can just take, write HTML tags and XML tags and specify exactly what you want to do. So I have another tag for XML func and assembly code, and I can see that the conditional reverse form payload is being injected to method public, blah, 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 run, and the injection is being performed using pre-inject. If, for example, I would like the same behavior to occur at the end of this method, all that I have to do is change in the configuration from pre to post, and that's it. .Net-Sploit will do everything for me. Remember, this is a very intensive task because it has to inject everything and perform line calculation, perform stack size changes. This is a very intensive task that he needs to do. Until it's finished, let's set up the attacker side. The attacker side contains netcat at port 1, 2, 3, 4, used for the reverse shell. So when a connection will come to port 1234 at the attacker machine, a reverse shell will be opened, right? So let's take attacker, put him over here. Let's see the progress going on at this side. Well, .NET-Sploit is almost finished. Well, next time I'll give it another little bit of memory so that it will finish sooner. But basically, it's pretty much at the end of the injection. It contains here, this is the workspace. In the workspace, this is where all of the interesting things happened, because now I have in input the original DLL. Decompiled contains all of the temporary directory in which files are being decompiled, changes are being made, and at the directory called output, this is where the information will be written. This is the new generated DLL that will be used. Well, in a couple of seconds, I will see that it's finished. Let me show you the executable that I'm going to use. Well, our mission, it's finished, great. So I can see that it's generated the DLL. And next thing is it asks me whether I want to generate the deployers. Well, remember, now that I have the DLL is not installed yet. I need to take the DLL and put it in the correct location. The deployers can do it for us. So I'm pressing yes. Please generate the DLL deployers for me. Now I have the batch files. And after that I have the batch files, I'm closing .NET-Sploit. I don't need it anymore. And I'm going to execute the sensitive application. This is just to show you how it looks like. This is the application. This is the trigger application. This is the application that I want to execute my reverse shell. So when sensitive application will be executed, and I see now that the UI of sensitive application, as you might see, if I go to the attacker machine, as you might see, nothing happened, right? The netcat port is still open because the connection has not been made, because I didn't deploy it yet. So last stage is when I'm running the same application, but only now I will do a deploy. The DLL is being injected into the correct location. Signatures are being disabled. The engine version of the DLL is being deleted. So basically everything is in place. By the way, if I want to reverse it back, I have another deploy file called undeployed. It will turn everything back to normal. So basically I have now the correct stage that I want. And now if I'll run the same executable, if everything worked as it's supposed to be, now a reverse shell should be opened on the left or the right side, sorry. A couple of seconds. Again, the virtual machine has a little bit of memory. And I got reverse shell. So now, let's go to the machine, to the attacker machine. And let's see if everything is fine. Let's look at the IP address. Well, I'm in the correct machine, 131, and who am I? Well, I'm administrator. Great. So basically, this is game over. This is when the machine is being hacked, it's been rooted, so basically the user will not see that it happened. Well, up until now, we've seen .NET-Sploit. We've seen .NET-Sploit that can be used to inject this kind of malware into machine-specific code. Again, this is not a .NET problem. This is a problem also for Java, also for other platforms. .NET-Sploit can be extended and can be used to perform other kinds of attacks. Well, now that we know that the problem exists, let's talk about what we can do to solve this problem, or maybe to raise the awareness a little bit and to minimize the risk that there is. Well, the first thing that we can do is that this is a call for action for antiviruses and host-based intrusion prevention vendors to block runtime tampering attempts. Well, the same thing that I would expect from a decent antivirus that detects that, for example, some process is changing my host's file, I would the same behavior I would like to my antivirus that says me, hey, some process is trying to change your .NET framework, or to some kind of process is trying to change your Java JVM. Well, this is just an example of runtime blocking. This is for prevention. This is for runtime. I'm also talking about IT departments, IT guys that performing, they're using file detection, file tampering detections, for example, tripwire. Well, just remember that it can be used on an external machine. It does not mean anything if you're running tripwire on the same machine that you're suspecting on, right? So basically, it should be used externally. I'm also calling for the auditors, testers, forensics, all of you guys that are doing security assessments or doing forensics. Look for evidence inside virtual machines. Virtual machines might contain malware. Okay? Virtual machine might contain the evidence that you're looking for. So don't just look at kernel level, at BIOS and all the regular stuff. Look also for a malware inside virtual machines. Developers should know that their application is secure as the underlying runtime virtual machine, because basically it all starts from the runtime. Virtual machine vendors, for example, Microsoft, Sun, all of the rest of the guys, well, of course, although it's not a direct problem of their virtual machine, basically if the attacker has control of the machine, well, he can do anything, right? But they can still raise the bar a little bit. They can make the life of the attacker a little bit harder. Although it's not a bulletproof solution, well, it gives us a little bit of security. And of course, end users, all of us, we should know that we should verify the runtime, and we should, for example, if we detect that something is going wrong, you can just reinstall it again. Well, more information can be obtained at the site applicationsecurity.co.il. In this page, you can download the slides, you can download the Whitepaper, Net-Sploit tool, source code, demos, basically everything is there. Just take it and basically talk about it and raise the awareness about problems like this that could happen. Well, another references that are important for me to mention, well, first is Ken Thompson. Well, this guy talks about C compiler backdoors back in the 80s. Talked about C compiler backdoors back in the 80s in which code is being injected into compilers. So even though the same thing that we saw, that developers that want to hide their malicious code at the application level, but they know that security audit will be performed, so they hide it in a virtual machine. Now malicious code, he talked about malicious code at a compiler level. And another guy to mention is Dennis Cruz from OWASP. Dennis, hi. Dennis talks about the dangers of full trust applications. He talked about it a couple of years ago, in which applications can change due to their high-level access to the framework, for the .NET framework. So, for example, applications can change their own memory space that can change the calls to the low-level virtual machine. Well, to summarize it up and to leave some time for questions, we've seen that malicious code can be hidden inside application-level virtual machine. We talked about it as an alternative place for hiding malicious code. This is another place besides the kernel level, besides the BIOS drivers and stuff like that. We are talking here about application level malware, application level rootkits. As an alternative place for backdoors, remember the example that I told you about developers' backdoors? It happens. Malicious developers hide backdoors inside code. Especially developers that are developing a very sensitive application, a finance application, a military application, stuff like that. Malicious code, managed code rootkits can lead to some very interesting attacks. Basically, as I said, it is not dependent on some specific technology. It does not dependent on some specific vulnerability. Well, if it was a vulnerability, there was a patch for it, right? There will be no patch for managed code rootkits. This is a concept. This is a concept that we have to deal with. And of course, as I said, it's not restricted just to .NET or to Java. Basically, when I first talked about, my first presentation about this topic was about .NET Framework rootkits, people thought that there was a problem in the .NET Framework. This was not the case. .NET was chosen just as a case study. And this is the reason why today I also showed you Java rootkits. And if I had more time, I showed you Flash rootkits or maybe some other languages. This is a concept that is relevant to managed code environments. And we've also seen Net-Sploit. Net-Sploit, a generic language modification tool. Well, I've showed you Net-Sploit, I've showed you in a sinister way of usage, but Net-Sploit as a custom language modification tool can be used to perform good things. Net-Sploit can be used to solve performance problems, to create minimized version of .NET Framework, for example, to make a hardened version of .NET, and basically it all depends on what you are doing. So, if you have any questions, I'll be happy to answer them. Guys, any questions? We have time. Yeah. You mean like if there was some kind of a problem like this in the wild? No, I haven't seen that. I haven't seen that. But the problem is that because no one talked about it before, there might have been some kind of problems before that, but no one would notice.
Do you need to have administrator rights to modify Whitepaper for .NET?
Yes. I mentioned it before that. I need to have administrator level privileges in order to perform this kind of modification. As I said, managed code rootkits are a post-exploitation attack vector. So basically this is where an attacker already has control of the system. He wants to keep control of the system. He wants to have some kind of a housekeeping technique. This is one way of performing MCR. The second is the trusted insider, the guy who already has access to the machine. Your IT manager, the developers, DBAs, etc., etc. Other questions? Well, if there are no other questions, thank you very much.